Still good morning. I am very happy that we are within the time schedule. I would like to introduce a little bit 6 presentations which were prepared by members of our department of intelligent systems. First 3, as a matter of fact, the department consists of several bigger or smaller groups. The first 3 presentations were prepared by the group of Peter Cadera, who concentrates the efforts of this group to optimization, planning, scheduling, simply industrial applications. The presentations will be given by Martin Macaš, by Václav Jirkovský, and by Sarah Strakošová. It's a PhD student which will present her interesting presentation from conference. And then the group of, let's say, nuclear physics, I would like to say active and partially radioactive. A group of Professor Škoda will present their new achievements. Tomáš Kořínek will do this. We will follow with the group of Ondřej Mamula, which is focused on control of energy systems, power plants, and so on. And you have had already part of this presentation by Mr. Šucha earlier. And the last, but not at least, presentation will be given by Jan Šedivý, who is the lead of speech processing team. So he will concentrate his efforts on building LLM. That's very hot topic of today. So you can see the very broad scope of interests of this department. I'm giving the floor right now to Martin Macaš. He will optimize in his presentation waste treatment.
Okay, thank you very much for the introduction. Hello everyone, my name is Martin Macaš. After those laser cutting and laser machining topics, I have slightly less sexy topic of waste management, but every little boy wants to be a dustman, so maybe it will be interesting, slightly at least. So I'm presenting a test before invest service which we provide to Municipality of Prague under EDIH framework. By the way, it's actually, okay, maybe next slide please. It's actually a very good use case. Yeah, very good use case for applying machine learning or data science, AI, because the municipality already has a lot of data. 7,000 containers are equipped with fill level sensors, and they really want to use it because they invested already. So we have data for like 1, 2, 3 years already prepared. The data infrastructure is already prepared, so everything is ready for applying those methods. And you can see here an example of signal, which is quite simple. It's just a fill level time series for each container. So this is one example. You can see the drop downs of the signal, which are the collections of waste. And I should show the whole flow chart, let's say. So on the left side, we can see the fill level sensing and data storage. The infrastructure is prepared, as I said. And what we do is actually should be on the right side, the final some decision making based on data. The decision making can be, for example, reporting. So sending some reports to sensor providers, some reports to collectors of the waste, the collector companies, or rescheduling the collections statically or dynamically. I will speak about that later. The dynamic optimization, the routing of vehicles that collect garbage is not part of the project, but will be future work probably. The main objective is to make the waste collection more efficient. I'm sorry. Make it more efficient. But to do that and to perform a good decisions based on data, we need a good data. So in the middle, you can see data interpretation, cleaning. We have to make data more trustworthy and more correct, and to interpret them and find different things, different mistakes and errors. So this is probably the most important part of the whole current project. Here you can see what we can detect, what can be the problem. Here is the simplest case of detection of data waste collections, which you can imagine is simple. But there is one false positive point, which is caused by error of the sensor. And those errors are normal, it's not so something very, not so very rare. So it can lead to some problematic decisions like the container, there was extra collection of the container, which is not true here. So this is an example, but there are many such examples and I don't have time for them. Okay. Here are some other things that we need to detect, and we are using heuristics, we are using also pattern classification, supervised learning. On the left side you can see, for example, stacked entry of the container, which can be a problem for citizens. In the middle you can see different peaks caused by error of the sensor. On the right hand side you can see a waste slide, which is normal, but we must differentiate it from sudden drop down, which are errors of sensors. So those are just little examples of many things that we have to detect, and behind those, or except of those, we also need to detect some other abnormalities. So we are performing also anomaly detections. Here is a very simple example from of a method well known from industry of Six Sigma anomaly detection, where we have like a weekly profile, mean weekly profile, and we have some standard deviations, and we define a range of plus minus 3 sigma, 3 standard deviations. And if some point exceeds this range, then it can be anomaly. Here is probably anomaly caused by first school day, but we also tried to test different other methods. The best performing method at this moment is based on autoregressive model with exogenous variables, where the exogenous variable is the collection signal, so a binary signal, where we threshold the error of the forecast of this model, but we also use autoencoders and threshold the reconstruction error of that. And we apply and test many of those things to choose one of those for further integration into a Golemio system, which is Prague platform. Okay, here you can see how we are trying to simulate what will happen if we change the schedule of collections. This is very simplified, by the way, but we have the clean signal at the beginning. We can compute its difference, and then we can remove the collections, and then this represents the deposit of the waste in every hour, and we can use it by cumulative sum together with the new collection schedule. We can use it to simulate the new schedule, the new fill level behavior, and we can use it in an optimization loop to optimize some criteria. An example is here. You can see that we can also simulate how much of the waste will not be deposited into the container because the container is full. It's the green part where we can measure the mist capacity and overflow, and we can also measure how often and how much the container was collected without being full, which means that we unuse its capacity and we waste fuel for collections or CO2 and so on. Both those criteria are in trade-off, but both have some ecological gains. It means on the left side we save fuel and reduce CO2. On the right hand side we reduce the pollution of neighborhood of the containers, for example. We have some KPIs which I will not go into the details, but first are the data cleaning KPIs, where we are able to automatically analyze the signals instead of manual analysis by expert. There are also optimization KPIs where we are able at this moment reduce those criteria by 10%. This is measured on 100 containers, and there are many other benefits which you should see here. Also, for example, I must point out the networking, because it enables better communication between the municipality and the other stakeholders like citizens, but also a collection company or sensor providers. And we had to develop an application which will not be used finally, but it's used for enabling communication and getting feedback from the customer, which can give us feedback about the methods, but also user experience, but also we can use it for evaluating the methods in terms of comparison of our predictions to what really happened to the real annotations. And those are examples. The user can optimize methods, can go through the signal, can optimize schedule of collection, can annotate data, and can observe the automated annotations. Okay, thank you very much. This is last example. This is a predictive maintenance case where if we detect a lot of sensor errors, we can predict that the sensor will die soon. So this is like 3 weeks ahead prediction of sensor death. So this is another application of this. Thank you very much. Finally, it will be selected methods will be integrated into Guardrails system, which is already existing. And that's probably all. Thank you.
So, okay, hello everyone. It's my pleasure to introduce or give you an overview about our project, contractual research with Škoda Auto company, and the project was about the weights of the special car equipment. So, for the first, some background to understand the entities from the next slides. Most of us have a car, and most of them, for example, me as well, have a car from Volkswagen concern, and maybe you can find in your car in a service book or on the tank cover you can find the car specification. It is composed of approximately 200 families of PR numbers. PR number represent production order number, production or product specification or part specification. For example, a GOC represents 5-speed manual transmission. So everything in your car is specified by a PR number, and when you compose all of the families, you have a complete specification of your car. Sometimes the PR number represent nothing. For example, you have a PR number for the car without sensor, next PR number for the car with a front sensor, and the next PR number from the same family represents both of the sensors from the front and the rear side of the car. Next, we have angles. It's something like a rule which tells you if this PR number from this family is used, then you have to use some other PR number from the different family. Okay, the target of the project was to estimate PR numbers weight increments with respect to the weight key. Weight key is represented by 4 families: the family of the engine, bodywork, transmission, and the last one is the equipment lines, I think. And the ultimate goal was to optimize overall process, because this process was conducted by one person, and typically it is relatively time-consuming, and he spent many hours during the weight specification, and it is difficult after some upgrade of the parts to do it again and again. So that was the goal, or the main goal, and also it is not just I don't want to, how to say it, just a pleasure for the Škoda company to predict or estimate the weight of the car, but it is caused from the legislatives, because you have the rule that the estimated and also produced car dispersion should be somewhere around 5%. They are really good in the estimation of the weight. They are somewhere around 3%, but still they have to be better in the precision. So the biggest issue is that it is not possible just to sum up the parts which belongs to the PIR number, because when you combine different PIR numbers, you have different parts. So to solve the problem, we use a SAT solver. We model all of the regals which are available for the car. There are technical regals, active regals. Technical, for example, if you have one type of engine, you have to have specific transmission. Active regals, like you have a car which is produced to the Sweden, you have to have a battery with a bigger capacity, etc. For example, for one car, it is around 12,000 of regals which specify or limit the given production, and we use a SAT solver to generate feasible car specifications and also select, they call it in Škoda Auto, weight-relevant PIR families. So I have already mentioned that the car is specified by weight key, and with the help of the regals, for example, 40 till 80 other families are dependent on the weight key, and the rest is the thing what is important for this project, or as input for us. Next, we implement something we call it weight dispersion analyzer, and I will give you an overview of the main steps. So for the first, we generate a set of PIR numbers from weight-relevant families. Next, we prune the solution space using a database, bill of material database in English, I hope. And next, we go to investigate these pairs from a family to get a weight contribution. Next step is to generate identical feasible combination of PIR numbers. So the car specification for the pairs from the previous step. Now you can see, so the outcome will be better became better with increasing number of such pairs of the car specification for the pair of the PIR numbers. Next, we compute the weight of an overall car, and then the weight difference between these two cars with the same specification but just with a difference in the given pair of PR numbers. We have the weight contribution, and after, I think in this step, we generate 10,000 this pair of the car specification for every pair, and at the end you can see the dispersion of the weight contribution, which is provided here on the in the figure. And there are some limitations that if the dispersion is bigger than some threshold, you have to specify or improve the dispersion with the usage of the additional PR number from different family. So in this step, we go through all of the other families to find out suitable one which provide the smallest dispersion. So to conclude, the solution was not limited or was not limited just by the target, but also it is limited by the processes in the companies and the systems and softwares which are available. So it means that the outcome was, for example, Excel sheet with a specific number of the lines, the most important contributions of PR numbers, because these contribution of the PR numbers is manually added to another system, etc. So, thank you for your attention.
Good afternoon. I would like to present you my first publication at conference IEEE Indin last year. The name or title of my publication is Product Digital Twin Supporting End-of-Life Phase of Electric Vehicle Batteries Utilizing Product Process Resource Asset Network. So the motivation of our work is actually something we encountered ourselves when we wanted to create a disassembly process for EV batteries. And the problem is lack of support from manufacturers for the end-of-life processes. To address this problem, we proposed a product digital twin, which for us is a digital replica of a physical product. So in our use case, EV battery. This digital twin accompanies the product from initial design to recycling or reuse, and it offers insight for each product based on its condition and usage history. So this digital twin offers lifecycle management for a product. To create such digital twin, we are introducing BIFLOW Product Process Resource Asset Network, which is a graph-based model extending the traditional PAN approach. We can see a generic model here. It combines products, the red ones, processes, green ones, and resources, combines them and creates workflows, which in a classic PAN approach is more like just for manufacturing, but we extended this approach in bidirectional flows for both assembly and disassembly workflows. Since we also know what processes need which resources, this approach can also support flexible and efficient planning for manufacturing and and the end-of-life operations. Key features of BIPAN is the bidirectional operation, as I already said. So integration of both directions in just one model. It supports forward the assembly, which can be manufacturing, and also the backwards disassembly, which can be recycling or remanufacturing for secondary applications of product. And also it enables design of repair workflows which combines assembly and disassembly. Also it complies with industrial standards like ISO 95 and also the automation ML. Here again we can see a simplified model of EV battery, BMW E3, in automation ML. So we created the BIPAN in automation ML, so it's readable for computers and for manufacturing systems, etc. And of course it supports the creation of the digital twin. Now I would like to demonstrate a repair use case which I find most interesting. Here we have the whole BIPAN for the simplified EV battery, and this is the workflow we are following. So first we are moving in disassembly way, since we reach the part where we can remove the damaged module and replace it with the new one, and then we move back in assembly way until we have again the whole EV battery. So to sum up, BIPAN-based digital twin for products provides efficient planning for several operations during the whole life cycle of a product. Yeah, thank you.
Thank you very much. So, hello everybody, my name is Kořínek, and I'm from the group of Professor Škoda. And I'm going to present one of the results of our research, and it was focused on multiphysics problems in nuclear reactors. And this is something we are doing under one project, which is in National Center of Competence. It's a Center for Advanced Nuclear Technologies. And where we have a sub-project which is focusing on some high-fidelity simulations using coupled codes, which we like to use for validation of macro codes, where macro codes are nowadays used for safety analysis of nuclear reactors. So this is the work which was published in one of the top journals, Progress in Nuclear Energy, and I call it's a swing journal because sometimes it's D1, sometimes Q1. Nobody knows. But it's one of the best we can publish there. In this case, we did some multiphysics. So it means that we coupled two problems. We coupled neutronic physics with thermal hydraulics. There are several reasons you need to couple because there are some feedbacks or strong interaction between each other. So what does it mean? Basically, what is going on with the fission and nuclear physics in influence of the results we obtain from the thermohydraulics. So it means that fission is influenced by temperature, density of the coolant, fuel, and so on. And because of this strong feedback, you can reach some problems with stability of the calculations. So that's why we focused on relaxations of those calculations and see what's the influence on the computational cost and accuracy of those simulations. So why we care a little bit, why we care about focusing on some computational cost and some accuracy? Because, for example, in nuclear reactor core, if we speak about reactor we have in Dukovany, you have more than 300 fuel assemblies. Each fuel assemblies contains 126 fuel rods, and fuel rods are composed with a fuel pellet and cladding, which basically encapsulate the fuel, and this is surrounded by the coolant. So it means that in the reactor you have something around 40,000 fuel rods you have to calculate. So for the Monte Carlo simulations, you need a lot of particles to simulate it, especially if you have 40,000 fuel rods. So in our case, we take a look on simple problem. We took one of the fuel rods, which was surrounded in the coolant, and we performed those couplet calculations using the high fidelity code. So for thermohydraulics, it was CFD, and for the neutronics part, it was Monte Carlo. And we take a look on the relaxation. As I said, there are a lot of strong feedbacks. So when you start to do it without any relaxations, you will basically never converge because there will be some oscillations in the solutions. So in this case, we focus on methods of the relaxation. So there are different methods using some constant relaxation factor, some factor which is changing during the iterations, and also some additional change when we increase number of simulated particles, basically to save some computational time. So basically, one of the results we take a look, because from the Monte Carlo simulations, you have some uncertainty of your results. So we observed like what is the change between the simulated particle, simulated particle histories, and how it will influence the uncertainty we are receiving from our simulations. So we saw that the most important, it's not linear. So it means that after some time increasing of particles, you will achieve some stable uncertainty. And another case, when we compare different relaxation methods, we saw that for some combinations you can reach convergence quite fast, but also it's after some cost. So when we start to change some particles, so we achieved basically within few iterations, but because number of particles influence the computational cost, so it's not so. It's important to take care about not only number of iterations, but also computational cost and especially accuracy. So just one example on the right side, there is a cross sections of this fuel pin. So on the left. There are after first iteration, so top is when we use the large number of simulated particles in the first iteration, and the down left is when we use not so many particles. So you can see if we are not using a lot of particles at the beginning, so there is a high non-uniformity because of we have poor statistics for this. But within a couple of iterations, you achieve quite better results in this case. So that was one of the outcomes. As I already said, if you have something around 40,000 fuel rods, and this was the case only for one fuel rod, and we still spent like 200 minutes. So even if you are using some high performance clusters to perform those calculations for the whole 3D model of the reactor core, we are talking about weeks. Especially for the multiphysics, maybe months, and that's one of the focus on the study. Take a look on a simple problem, and result will be propagated on those large-scale simulations. So that's all from my side. Thank you.
Thank you.
So my name is Mamula. I'm head of energy group under Professor Mařík. And I will present you a success, we call it success story of research and development in our department. Okay, it's the wrong direction. Last year on this spot, I presented that we had developed an algorithm which will be implemented in the real application. Since then, you might have read, the time passed through the winter, early summer, into the summer, and then maybe in June or July, I think you might read some articles about the go live of the power plant, and there was several official starts and conferences on the spot presenting that the investor achieved this goal. And the operation was put in the power plant was put in the operation. What was the timeline of the project? We met with the investors approximately in 2019 and started to think about their concept. We provide them with the initial feasibility study. providing insight if one big engine or more small engine are feasible for their idea of provision of ancillary services, and then we came finally to the solution of 6 small engines and the battery system, which seemed to be ideal. Then was a not paid time of the idea so growing, within which we pushed the investor to go with us into the project supported by the Technology Agency of Czech Republic, and the algorithms has been developed within this project. Not at the end or after the end of this project, but within this project we have started the implementation, because we had to put the prototype of the algorithm into industrial application. And in July 2024 we started operation. On 15th of July we went into real operation, and in May we successfully passed with the first generation of the algorithm certification. So we were certified that the algorithms is compliant with rules of TSO on provision of ancillary services. And then we implemented some missing parts, and we started the operation. The power plant since then is in full operation on 30 megawatts. Nowadays it was get up to 35 megawatts of power provided within the ancillary services, and we have not any stop or malfunction caused by the algorithm. So we are, I think, successful from this point of view. I will quickly respond to the question about the money which are connected to the project. I just remind you what's inside the power plant: 6 more generators driven by aeroderivative gas turbines, accompanied by battery system. In total, it's 55 megawatts, but we combine it up to 35 megawatts to keep some quality rules of the provided services. And the system, the control system, is embedded into the Siemens system. Our algorithms works as the Docker container, and is composed by several autonomous pieces of the algorithms, which tries to interpret the commands from the TSO, tries to find the best number of machines to be run, checking the healthiness of each component, and maybe stopping to command them and asking for another one. And we are still developing the pieces of the algorithms to increase the efficiency of the control and increase the robustness of the control. In terms of money, I will get back to the timeline. Sorry. In the term of the money, of the implementation, the implementation was supported by the contract with value of 3 million crowns. Now we are negotiating about the follow-up contract in enhancing the services for next 1.5 million crowns, and on the table are other features which might be in 2 or 2.5 million crowns within year 2025. So I think this is a really big success of R&D implemented into the real operation. If there is a spare time, I can show you instead of digital twin, I can show you the real operation of the power plant. So I'll try to connect. Okay. Tak asi se Okay, so next time, if you are interested in, I can show you the real operation of the power plant, because I'm not connected. I'm right now directly connected to the control system of the power plant, so we can see what's happening inside. Just to imagine or help you to imagine what money are we talking on the investor side. I say our because I'm from the 1st of January are on part-time job within the investor, responsible for the operation of the power plant. So the best 15 minutes we made within the operation of the power plant was time when the regulation energy, which is produced by the power plant, was the cost of the regulation energy was 12,500 euro per megawatt hour, and on full power on 35 megawatts within 15 minutes we made 2.5 billions. If the algorithms would work bad, we might lost 2.5 millions because the penalty is approximately the same size against the revenue if the power plant doesn't work well. So this is the business we are working in. It's really tough and sometimes is exhausting, but I think that we are proud that the algorithm is working for most of half of a year without any malfunction. Okay, thank you.
Thank you.
Hello everybody, my name is Šedivý and I am running here a small group working in the NLP, so I'll bring you from the massive money and big energy to very software-like area, but as you may noticed in the news, this area is also spinning enormous billions in the US, billions of US dollars, and it is really developing very fast. So let me first tell you something about our department. In the last year, actually, many students who were working with us for several years left, 2 PhD students and some other MSc, etc. So we are at the moment restructuring the group and looking for new people working with us. We were left with only 2 PhD students, and another student is joining us next month, and we have several contributors from the staff members from CIRC. And while changing the staff, we are also opening new areas, and as you may know, we have been working for several years with Amazon, and we were competing with our dialogue systems. So now we are continuing to work with Amazon on a new task, which is developing language models, generating Python code, but ensuring not to generate malicious or vulnerable code, meaning that if you would ask how to do DDoS on CNN, we must reply, no, we don't allow that. We won't generate anything. Just to complete this page, I just skipped the partners we work for or we worked for in the last year. As you can see, we had several business partners, starting with Porsche, Seznam, T-Mobile, and currently we work for a Ministry of Finance. All these cooperation with these industrial partners are thanks to what we have done in research, because what we deliver to these companies is basically what we started to work on 2 years ago. So currently the Ministry of Finance is a retrieval augmented generation system using several algorithms which have been partly developed here at CIRC, and the combination of these algorithms or the whole architecture, it was fully developed here, and we are now in the phase of deploying it and testing it. But let's go back to what we will do in the, oops, I have to do it the other way around. So the Amazon Trusted AI. So as I explained, the basic idea is to generate non-malicious code and not only show the code, but also to explain how the code has been developed. There are already applications on the market, like which you can definitely install on your machines, like Copilot, and some other businesses are developing these systems, and the basic idea or the basic way how to make sure that we don't listen to something which has some not very politically correct idea is to create a system which is depicted here on this picture. So there is the question, and then the first thing we do is we use a smaller language model which has around 1 billion parameters, and this language model is used as a classification machine, meaning that we have only one output, and the output is a probability of the answer being correct or being incorrect. Based on the correctness, we decide whether to call another larger language model, in our case around 8 billion parameters, and we generate the code if the question is okay, and if the question is considered to be not correct or to be malicious, then we call the LLM with a different prompt and ask the system to generate something like, I apologize, but I cannot generate code like this, etc. So this is the simplest way, and most of the, as far as we know, because not everything is published, most of the developers are using very much the same scheme. So our task is to, first of all, train or design set for training the classifier, and then design set of tests of training sentences for training the large language model. Luckily enough, we have, thanks to AWS, a lot of resources on GPU cards, so we can actually use a lot of time and train it. But the key question is, do we have the right training sentences, meaning having the test which really shows good Python code and not very good Python code, and how to use these training sentences to improve our language model. These days, many of these training sentences are generated by language models, so we are developing now these days systems for generating training sentences, and it is well known that these synthetically generated training sentences are further improving the LLM which was generating it, which is recursion, and this may ultimately lead to singularity or creating systems which are better than humans, and currently it's a hot discussion or hot topic discussion on all these social networks, within what time we would reach the singularity. So this is our program, or this is our vision for this year, and certainly the main vision which is behind learning how to develop these things and how to research new systems or better systems is to actually develop application which would help our industry here in the Czech Republic to make many of their activities, specifically the administration activities or activities processing data, how to make them more productive. This is what we are doing these days in the Ministry of Finance, and keep us your fingers crossed so as we succeed, and it will bring us new partners and new opportunities. Thank you.
Thank you.